Welcome to another video explaining the universe using the particle model. Well, today's video is another video in this series on the diodes. This one in particular is the Zener diode. I have given several videos including the light emitting diode and the photoelectric effect, part 1 and part 2. If you haven't watched those, I recommend them, and they will help explain some of the things I might be saying today that you have not heard about. Here's a description of a Zener diode from Wikipedia. A Zener diode is a type of diode that allows current to flow not only from its anode to its cathode, but also in the reverse direction, specifically when the Zener voltage is reached. Zener diodes have a highly doped p-n junction. Normal diodes break down with the reverse voltage too, but the voltage and sharpness of the knee are not as well defined as it is for the Zener diode. Normal diodes are not designed to operate in the breakdown region, whereas Zener diodes operate reliably in this region of the diode. The structure of the Zener diode. This is a physical structure from this link. And here they say the doping of the Zener diode is somewhat higher than normal. The other one said very high. I think it's my opinion, because I'm not an expert in doping, but that the Zener voltage itself is somewhat determined by how highly it is doped, or it may be somewhat less, somewhat more, giving different voltages. And this is a diffusion diode. It's built by diffusion process, where you take a substrate, a silicon substrate, and diffuse the p-type doping into it, and then on top of that, into that same substrate, you diffuse the n-type doping. And that's a general one. And you got the metallic connection for the anode and the cathode. And here is a basic, simple Zener diode voltage regulator circuit. Here's pictures of diodes as they might appear physically on a circuit board, with a stripe at one end indicating the negative side of the Zener. This is the symbol, just like a diode, except it has the negative line bent at two ends. You can actually think of that as a Z for a Zener. So this is a voltage regulator that takes an unregulated voltage input, DC, and converts it to a regulated output at this point. And so if you had say a 9-volt battery here with a current limiting resistor into a 5-volt Zener, then these 2 points would be clamped at 5 volts. And this loads, the circuit would see a reasonably controlled 5-volt voltage, varying somewhat over load. It's a very simple circuit, but inefficient in the fact that the more current you draw, the more power you waste in that resistor. A simple example of creating a cheap, inefficient reference. And so if your circuit internally needs like a 2-point reference for an op-amp or something, then you can use a Zener diode to establish it, as long as it's not critical overload. This is the Zener IV curve, the current voltage curve, and the voltage on the horizontal axis and is in volts. Although this scale is expanded so we can see this curve better. And the vertical line is for current, it's in microamps. So we're talking about a very small amount of current. As you increase the voltage up here to 0.5, it starts to break away. You only have 1 microamp of current here. Same thing with here. You have a half a microamp of current to get to this part of the curve. And then there are 2 breakdowns. And we're going to talk about both of these. There's the Zener breakdown, which is its operating point. up and down this line. And there's the avalanche breakdown that happens, and we'll talk about both of those. In case this is the avalanche breakdown, and from this link, we're told that p-type and n-type material together forms the p-n junction. The depletion region develops at the junction where the p and n-type can connect. Their width depends on the bias applied to the terminal of the p and n regions. In other words, the voltage. It depends. The width depends. It gets bigger and smaller depending on the voltage. As the reverse bias increases, the electric field across the depletion region increases. So I think it gets wider. I think that's what they're saying. When the high electric field exists across the depletion, the velocity of the minority charge carriers crossing the depletion regions increases. The velocity increases. Kind of interesting they say that, because that's part of how I describe it in the particle model. These carriers, we're moving at high, collide with the atoms of the crystal. Because of the violent collision, and we're talking now about the electric field is quite high. There's the free electrons are moving through, hitting atoms very hot, probably getting hot. Okay, this violent collision is probably causing heat and them to be atoms to vibrate, and the charge carrier takes out the electrons from the atoms, and this can be destructive and damage the diode. So you don't want to operate it in this region, but this is a feature that seems to happen when you apply a reverse voltage. Okay, so here's the IV curve for a Zener, especially for a Zener, but I'm pointing out that the normal signal diode that you use in circuits operates up here in the first quadrant with a positive voltage, and you get a positive current. Zener diode is operated in the reverse direction, and basically you want to get the voltage high enough, like 5 volts, such that it's operating here in this region, and even though you're increasing the voltage slightly here, it maintains this 5-volt reference, plus or minus a certain amount. Photodiode actually works in this region. They get a lot of use out of a diode. It's functionally in circuits very useful things for many different things, and this will be my next video. The Zener breakdown is exactly where we want to operate the Zener diode, and the breakdown occurs in the very thin depletion region. Thin depletion region, one part of the explanation in terms of avalanche, it looks like you're getting a wide voltage and maybe a wide region. This says, no, it operates in a very thin depletion region. The thin depletion region has more numbers of free electrons. I almost wonder whether they wrote this wrong. The reverse bias across the p-n junction develops the electric field intensity across the depletion region. The strength of the electric field intensity becomes very high. Like I say, this seems to contradict itself in my mind here. The electric field intensity increases the kinetic energy the free charge carries. In other words, they start moving pretty well. These energetic charge carriers collide with the atoms in the p-type, n-type material and produce electron pair holes. And of course, then you have holes going one direction and electrons going the other direction, and that's the current flow. Okay, the reverse current starts flowing in the junction because the depletion region entirely vanishes. Okay, now they're saying again it's very thin. It's thin, now it's gone. And it's very, very small. And this process is known as the Zener breakdown. In other words, the energetic charge carriers produce electron pair holes. They hit other atoms, breaking away an electron, leaving a hole in the atom, and the holes move and the electrons move. Okay, so here's a schematic of this standard model for a Zener. And this is the particle model for the Zener. Now, they say it's a thin region. I looked and looked for a thin region. A diagram that gave me a thin region and then showed that at breakdown there was no depletion region. Couldn't find it, so I just picked one. Most of them have some space here to allow you to see it's even there, I suppose. But again, this is in reverse bias mode. The plus is tied to the negative side of the Zener, and the minus is tied to the positive side. The plus pulling the electrons this way, and the minus pulling the positive this way, creating this depletion region. This is in reverse, and it generates an electric field. Very simply, a positive particle to a negative particle, the field is always shown from the positive to the negative. I drew that arrow in myself in the word, showing that's the direction of the force. And if you current flows this way, but electrons flow this way, and you can see that the force, the E field, assists the flow of electrons in this direction. That's the standard model. The particle model, this is very similar to the one I showed in the previous videos. There's the Zener made with P-type doping and N-type doping, and they're doped more than a normal diode. So when you add the doping, you're creating extra G1 particles. These are like, in a sense, extra electrons. It's more negative. By adding G1s, it's more negative. By doping it with a different doping, you reduce the number of G1s. Okay, there's a G2 force field, and these are arrows showing G2 particles coming at the Zener diode, setting up forces at each point. The force at this point is equal to the force at this point, and it varies as you go through. Now, since there are more G1s here, there is more loss, and the loss to the equal point happens sooner because there's more G1s, there's more G2 particle loss here as it pushes on the G1s. But here there's fewer, it takes longer, so these 0 point to the equal point here where the forces are equal. This is like the center of the Earth, if you will, except it's not, since this is unequal, it's the 0 gravity point isn't here. This is like a 0 gravity point here. So you're going to build up this G2 gravity field inside the diode. You're going to have a force in this direction up to this point, and you're going to have a net force in this direction up to this point. So as the diode sits there, it already has this bias. It's built in because of the imbalance of the caused by the doping. But as soon as you start bringing in G1s, this G2 force field accelerates the G1 particles till they get to this point, and then they slow down. But in any case, they go faster for a while, then they slow down. The average speed inside is faster, and it's that speed that causes them to more easily get through than normal. That causes that slope on at the breakdown. The more G1s the more voltage you apply, the more G1s are being emitted. The more G1s causes a greater G2 gravity field around the diode, and this is a greater force. It moves them faster. And again, the faster they move, the less they hit, which Otherwise, they would be hitting. So this is the model for the TPM model for this Zener. And this speed is the primary reasons why this stays this direction. And you would normally think, like in a resistor, it would go out here, but it's doped heavily. When it's got a lot of G1s flowing through it, it passes through very easily, just like asteroids passing through our galaxy can pass through easily because of the wide open space. And the faster they go, the less chance they hit, which is exactly what happens with the Zener diode. This is an area of the photodiode. I'm having trouble with this one, so we'll see what happens in the next video. But really, this action is almost opposite to this action. Here you have a large voltage increase with a small current. Here you have a small voltage increase with a large current. It's actually behaving quite differently. So we'll cover that next time when I cover the photodiode. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.